All right, welcome everyone. I'm your Eduvos lecturer, and today we're diving into an absolutely crucial part of modern software engineering, resilient systems design. We're going to be mastering chapter 14 of our text. Now, before we even look at a single line of code, I want you to internalize our core philosophy for today, and that is we expect our systems to fail. Perfection? It's just not the goal here, mostly because it's impossible. Instead, our aim is to engineer systems that can take a real hit, protect their most important functions, and bounce right back. So grab your notebooks, because this stuff is essential, not just for your exam prep, but for your entire future career.
Here's our roadmap for the session. We'll kick things off with the reality of failure, then move into identifying critical services. After that, we'll look at survivable systems analysis, followed by business-driven resilience. We'll then apply all of this to a real-world example by architecting the Mentcare system, and finally wrap it all up with a master recap.
Section 1. The reality of failure. Let's just go ahead and accept it right now. In modern engineering, perfect code is a total illusion. So let's establish a baseline definition that's going to anchor everything we talk about today. Resilience is a judgment of how well a system can maintain the continuity of its critical services in the presence of disruptive events. You know, a really common misconception, especially among junior engineers, is thinking resilience means preventing failures entirely, but it doesn't. Resilience engineering assumes that avoiding failures is literally impossible. Instead, we're focusing on surviving, limiting the damage, and recovering. It's not about magically dodging a cyber attack or a hardware fault. It's about making sure the whole system doesn't completely collapse when those things inevitably happen. Section 2. Critical services. This brings us right to the concept of system triage, because when a system goes down, you simply cannot save everything at once. Okay, let's dive into this. When the whole system is on fire, what do you say first? We need to define critical services. These are the essential elements of a system that allow it to fulfill its primary purpose. Before you can even think about building a resilient system, you have to pinpoint these services, because these are the exact components where you're going to spend your time, your effort, and your budget to protect.
Let's apply this to a real-world scenario, and definitely make sure you understand this distinction for your exams. Imagine a software system that handles emergency calls. On one side, we have a critical service, dispatching an ambulance to a medical emergency. On the other side, a non-critical service, logging that call data for a monthly management report. If a server goes down or there's a cyber attack, we have to maintain the ability to dispatch that ambulance at absolutely all costs, right? Human lives are literally depending on it. That monthly call log? Yeah, back and wait until the system is fully reinstated. We always sacrifice the non-critical to ensure the survival of the critical.
Section 3. Survivable Systems Analysis. So we know what to save. Now, how do we technically go about saving it? Let's look at an approach from the U.S. Department of Defense. This technical method is called Survivable Systems Analysis, and you'll definitely need to be able to list these exact 4 stages in your exams. Step 1 is system understanding. This is where you deeply review your requirements and your overall architecture. Step 2 is critical service identification. Just like our ambulance example, you figure out exactly what must be maintained. Step 3 is attack simulation. Here, you're identifying scenarios or use cases for possible attacks that could compromise those specific services. And finally, step 4 is survivability analysis. This is where you identify the system's soft spots and propose concrete strategies for resistance, recognition, and recovery. And this brilliantly illustrates how those 4 steps actually connect in practice. Notice how it's represented as a continuous cyclic process. You don't just do this once and walk away. As your system evolves, or as totally new threats pop up, you have to continuously review the architecture, identify those critical services, simulate attacks, and propose new survivability strategies. It's an ongoing, never-ending cycle of defense.
Moving on to Section 4, business-driven resilience. Because, let's be honest, the military context doesn't always translate perfectly to the fast-paced corporate world. See, the Department of Defense method kind of assumes you have this perfectly detailed requirements document before you even start building. But in modern commercial software engineering, agile teams are moving incredibly fast, and they rarely have perfect requirements. So we use a more general method containing these 5 interrelated streams. First, you identify business needs rather than just strict technical requirements. Second, you plan system reinstatement so the business can actually get back to normal operations. Third, you identify the specific critical assets that deliver those critical services. Fourth, you plan for the quick recovery of those exact assets. And fifth, and this is absolutely crucial,
You must test all aspects of your resilience planning against simulated failures. If you don't test it, you really don't know if it works. Section 5. Architecting mental care for resilience. We've covered the theory, so let's move into practical application and see how architecture physically creates this resilience. You might remember the Mentcare case study from earlier in the course. It's that patient information system used in mental health clinics. What we're looking at here is the standard client-server setup. The local clients connect over a network to a central server, which then talks to the patient database. But ask yourself, what happens if the network suddenly goes down? Or what if a cyber attack completely takes out that central server? Under this standard architecture, the entire clinic just stops functioning. The doctors literally cannot see who is at risk, and, well, that is a catastrophic failure of a critical service.
Now, what's really interesting about this upgraded approach is how we alter the architecture to create physical resilience. Specifically, we introduce local summary patient records. By architecting the system to automatically download a summary of scheduled patient records to a local client computer every single morning, we create this massive defensive buffer. If the main server gets taken offline by an attack, or say the clinic gets hit by sudden load shedding and the network drops, the doctors can still actually function using that local data. The critical service is maintained. Plus, we add a backup server and a database integrity checker to automate the recovery process. This is exactly what it means to architect for resilience.
Section 6, Chapter 14, Master Recap. Let's bring all this theory and practical application together so you're ready for test day. All right, let's get into a rapid-fire recap to get you fully prepped. Get those pens ready. First up, remember that core definition. Resilience is all about maintaining the continuity of your critical services. Next, you need to know the 4 R's of resilience engineering. Recognize the problem, resist the failure, recover critical services, and reinstate the full system. Third, understand the Swiss cheese model. This basically means resilience is a socio-technical issue. You need diverse, multiple layers of defense, both software checks and human operator awareness. That way, if a threat slips through a hole in one layer, another layer catches it. And finally, process flexibility. Now listen closely to this one. Over-optimizing a system by automating absolutely everything and removing human operators can actually destroy your resilience. Because when unprecedented, really weird things go wrong, you need flexible human beings who can bend the rules and adapt on the fly to save the system. I want to leave you with a final thought as we wrap up this review of Chapter 14. Anybody can write code that works on a perfect machine in a perfectly controlled laboratory, but engineering a system to survive the absolute chaos of the real world, that is what makes you a true professional software engineer. Next week, we'll be moving into Chapter 15 on cloud architecture, where you'll see how these exact same principles of resilience scale globally across distributed servers. So, as you study this week, I want you to ask yourself, the next time you write a piece of critical software, are you just going to assume it'll work flawlessly? Or will you actually have a solid plan for when it inevitably breaks? Good luck with your exam prep, and thanks for joining me for this explainer.